We're back at graphs of motion, and although you've done some of this in grade 10, we need to revise it before we move on to a little bit more complicated graphs where we're going to look at vertical motion, but also before we're going to look at equations of motion. Now, what you're seeing on the board now is a summary of the definitions that you basically learned last year, and it is in your notes, so don't worry about it. It is in chapter 1. So you can see these definitions are there, and you need to be able to remember these things again. So you need to define distance as the length of the path traveled. You will remember we had a little picture where someone went from school to their house, and the distance was the total path traveled, where the displacement would be as the bird flies. So if I was going to draw a line straight from there to there, and now you also know that that would be a vector quantity and that would be a scalar quantity. So you've learned a bit since we've done that. Displacement is then the change in position. We started there, we ended there. That's your change in position. We also looked at the rate of change of distance, and we defined that as the speed. So distance over time was our speed, and displacement over time was our velocity. So the rate of change of displacement, or the rate of displacement, or the rate of change of displacement, it really doesn't matter which one you use, was defined as our velocity. We are going to look a little bit more detail at average velocity and instantaneous velocity. You dealt with that a lot in ticket timers, and we are going to look a little bit at the concepts that you used in ticket timers, but we're not going to do ticket timers again this year. But the concepts that you need for this year, I'm going to revise with you. And then we still have acceleration as the rate of change in velocity. Now, these equations we're going to look at a little bit later when we're doing the actual equations of motion, but we need this before we can start talking about graphs of motion. So if there's any of this you don't remember, please put your hand up and let your teacher explain this to you in a little bit more detail if you forgot any of this. I'm hoping that this is easy for you because you've done it in detail last year. Now we're going to look at graphs of motion, and the same thing. You've done lots of this last year already. You've drawn position versus time graphs. You used the ticket timer to do that. You also drew velocity versus time and acceleration versus time graphs. You actually already interpreted it. So I'm just going to look quickly at examples where I revise what you did there. And then we interpreted it. And this is the important part where you interpret the graphs of motion and look at the gradient or the area under the graph. When we say area under the graph, we actually say it wrong because we should say the area between your line and the x-axis, because it's not always under the line. And I'll tell you more when I have an example. I'll show you what I mean there. We're going to be looking at velocity time graphs. We're going to look at acceleration time graphs, and we're going to look at position time graphs. You've done all of this last year, so like I said, just revision. So let's quickly look at the different graphs we can get. Firstly, we're going to look at displacement time graphs. So displacement, we're going to still use S. You will see in some textbooks they use delta X, or they even use X to just show the position. It really doesn't matter. You must just know that it's the position or the displacement versus time graph. So we're going to have an S there, and very important, a graph means nothing without a unit. That is still very true for all graphs. So it's displacement versus time. There are a few options here. We are going to deal with changing displacement. Yes, we can deal with changing displacement. So that means an object is moving. It can be moving at a constant velocity. That means in every time interval, they change their displacement by the same amount. Now, this I'm not going to do in so much detail because you guys did do this in detail last year. So that would mean I'm getting a straight line graph, which shows that in every time interval here, I'm covering the same distance. Remember, distance and displacement is virtually the same thing. The one just has direction and the other one doesn't. So that would be an object that's moving forward. Remember, we're going to see positives as forward or north or south. Look at what the question tells you. And only when it comes down again, it's turning around. Also, make sure you know what graph is given, because that's different on a velocity time graph. So now this is one option we can get. If an object is just standing still in one place, that means its displacement isn't changing. So let's say an object has moved 5 meters and now it's just chilling there. It's not moving at all. So that means the graph will just be a straight line at that point. Now think for yourself logically, what is this object doing? It's staying at 5 meters. So its displacement is constant, which means it's not moving. So its velocity must be 0. That's the second option. And then we do have objects where they can be speeding up or slowing down. Now, if an object is speeding up, it means that in a specific time interval, it's going to cover more distance. So that means if I'm covering this much distance in this time interval, I might cover that much distance in the next time interval and that much in the next one. So, oops, that's a very skew line. So you did this last year and you saw that we can get a curve that's curving up if the distance that it travels per time interval is increasing, or a curve, it could be curving down like that. Now we need to look at what we can use of this graph. If I have a displacement time graph, I can either, always, when you have a graph, you can either use the area or you can use the gradient. If you forget in an exam because you're now stressed which one is which, just go and look what is area. You know area is length times breadth, and you know gradient is change in y over change in x. Now, if you look at the length times breadth, it means it's going to be, if we look at this area here, it's going to be seconds that we have here on our x-axis times by meters here. Now, if you have anything that we measure in meters times seconds, please tell me, because I don't know of any quantity that's measured in that unit, meters times by second. So actually, for this graph, the area would mean nothing. So we cannot use the area of the displacement time graph. But if we look at the gradient now, it's y over x. So let's look at the unit on our y-axis. That's meters. So we have meters at the top and we have seconds at the bottom, which gives us meter over seconds, which is the same as meters per second. And now that sounds more familiar because we know that we measure velocity in meters per second. So displacement time graphs, the only thing that you can use of a displacement time graph, except for logic, because you need to always think what the object is actually doing, is the gradient. So the gradient of this displacement time graph will give me meters per second, which is my velocity. And that's our first graph done. The second graph that you can get is then the velocity time graph. And this is the one that they ask the most in most exams, because the velocity time graph gives us the most things that we can test you on. So if I look at the velocity time graph, there's also a few options. Please remember that in school, we only ever going to look at constant acceleration. Just keep that in the back of your mind. I'm going to come back to that now. So velocity is in meters per second, and you've done a few of these graphs last year, and time is in seconds. Now we have to look at the options we can get. Like I said, we only have constant acceleration. So that means in a certain time interval, again, if the velocity is increasing, it must be increasing constantly. So if it increases from 0 to 1 in the first time interval, it must increase from 1 to 2 in the second time interval. My line is a little bit skew, but I'm sure you understand what I'm trying to say. So you could have a straight line again. So a straight line, which means my velocity is increasing, but it's increasing constantly. So it will be a straight line because my gradient is going to be constant. That's the one thing I can get. I can still get a constant velocity. Now, please, now this is where I want you to see the difference between these two. Because here, when I had my displacement time graph and an object was standing here at us, I'm just going to make a 6 because otherwise I look like my S's, is at 6 meters, it means it's standing still because it's now at 6 meters. And at 5 seconds later, it's at 6 meters. And at 20 seconds later, it's at 6 meters. So it's not moving. But for this object, if it's going at 6 meters per second, it is moving. It is just moving at a constant velocity. So it's not increasing its speed or decreasing its speed. But please don't say that it's standing still because it's not. It's moving at 6 meters per second. All right. Now, if I look further, now this is basically all I can get, except I could get that where an object is slowing down. So when an object is slowing down, all that means is that my velocity is going to decrease. So I would have something like this, where my velocity was here close to 6, and then it decreases that it comes down here to 0 again if it stops, or close to 0 if it's just slowing down. So that's what you need. Just think about the object logically. Is it speeding up? Is it slowing down? And that's where I need to mention the bottom here as well, which I didn't draw here, but let me just make a quick axis here. If I have a velocity time graph and I have a line underneath, if I have something that goes underneath the line, please think about it logically and don't just write weird things down, because here the velocity is 0. So that means it's standing still. Here the velocity for our example was 6 here. So if its velocity is 6 here, as the time went on, it slowed down, and stopped. Yeah, yes, it's negative, but it doesn't mean the object is slowing down. It was at 0. You can't go slower than 0. So if I am at 0 and then I'm going -1, -2, -3, I'm still speeding up. I'm just speeding up in the opposite direction. And this is where you now need to remember your knowledge about vectors. Because if this was east, then this will be west. So please, like I say, always think what the object is actually doing in real life. So now, what can we use of this velocity time graph? We need to think about it again. Remember I said you can either use your gradient or you can use your area. So let's see, what does our gradient give us this time? If we look at our gradient, again, it's y over x, or change in y over change in x. I just want you to see the units. If you forget in an exam, you can always use this method. So we have meters per second on our y-axis, and at the bottom, on the x-axis, we have seconds again. And you should all be very good at math, so you end up getting meters per second to the -2. And hopefully you can all recognize this as the unit of acceleration. So the gradient of the velocity time graph is going to give us the acceleration. Now let's see, does the area give me anything? So area, again, if you look at the area, we say area under the graph, but remember it's between your line and the graph. So if we look at this area here, area would just be equal to length times pi breadth. So we have meters per second again. And this time we are timesing it by seconds here. Now remember, seconds, if there's nothing there, you might as well write a +1, and we end up with meters. So you can see now that this area under the graph would give us the displacement. And we are going to look at examples on how to draw graphs from other graphs. But if you have the displacement, you need to think, is it in the positive direction or is it in the negative direction? And I'm going to go through an example how to draw a displacement time graph from a velocity time graph. Now the last one that we have to look at, and yeah, I've still got a clean page, is an acceleration time graph. And I don't know why people ever lose marks for this, because acceleration, we already said we're only going to have constant acceleration. That means my acceleration can't change. It can change between time intervals. But if I'm looking at movement from 0 till 5 seconds, I cannot have a curve ever. I cannot even have a line going up and down. If you look here, displacement is the only one that could be going up because the object could be speeding up, or could be curving down because the object is slowing down. Velocity will always have straight lines because we're working with constant acceleration, and the gradient gives us acceleration. If we're looking here, it only ever must be constant. So if it's 6 meters per second squared, and you have to write here meters per second squared, even if it's a sketch graph, we still put our labels and our units. You don't have to put a heading, but the label and the unit must still be there. So all I can have here is either positive. So that's all you need to decide. You need to decide, is my acceleration positive? And then it's going to be a straight line there at 6, positive. It's always going to be horizontal to the x-axis. It could be negative. So let's say from 5 to 10, the object is slowing down, or it's accelerating in the opposite direction. And then it could also be where the velocity is 0, and this is the one you need to look out for. When velocity is 0, or velocity is constant, your acceleration will always be 0. Because remember, if there's no change in velocity, there is no acceleration. I'm hoping that this is coming back to you from last year. And just to make sure that it is, we're going to quickly work through 2 examples. Your teacher might stop and let you do it. Now, I actually don't think so, because it is, I've got other examples for you to do. So I'm just going to quickly look at these 2 graphs and talk you through it. So if you look at this graph, I don't think you can see it. So let me quickly make it a little bit bigger there. So if you look at this graph here, you can see that it's a position time graph. So as soon as you get a graph like that, you have to ask yourself, what can I use of this graph? Do I use the gradient? Do I use the area underneath the graph? And you should remember that for the position time graph, it's only meters per second that makes sense. So it's only the gradient I can use. Now, if I look at this graph here, it is the position, the gradient is not constant. The gradient is increasing. So therefore, my velocity is increasing. If you look at this little bit here, straight line, if you want to make sure it's a straight line, put your ruler on it, then you know it's a straight line. So for that little bit straight line there, my gradient is constant, therefore my velocity is going to be constant. There's a little bit of a curve again, my gradient is decreasing, therefore my velocity is decreasing. Here you can see if I was going to draw a gradient here, the gradient here would be 0. So therefore, again, my object is staying in one position, so there is no velocity for that little bit there. And then the object is moving again. My gradient is constant, so my velocity is constant. Please, it's not slowing down. It's actually speeding up because now I have a velocity again. But my object is moving closer to the 0 position where it started. So here my object turned around and came back to its original position here. So if we look at the questions, between 2 and 4 seconds, we already said between 2 and 4 seconds, it's a straight line. So it's a constant velocity. And you can calculate it using the gradient. And you can go and do that at home. We're going to do other examples. Then between 6 and 7, you can see it's a straight line there. So the velocity was 0. And then between 8 and 10, straight line there. Now, just one thing I need to mention, and this is what you need to remember from ticket timers. If I ask you for the instantaneous velocity, it is the velocity at that specific point. So that would be easy if I ask you for the instantaneous velocity at that point, because it's part of the straight line and you can go and get the gradient and you know what the velocity is. The same here, if I ask you for the instantaneous velocity at that point, or at 9 seconds, for instance, you can go and get the gradient there, and you know that is the instantaneous velocity. You just must make sure you mention direction. If this was east, if this object was traveling east here, It is traveling west here. Keep directions in mind now because you've done vectors. But now, if I ask you for the instantaneous velocity at a point where there's a curve. So if I ask you for the instantaneous velocity here at about, if you look here, between 1 and 2, it's curving. So if I say, what is the instantaneous velocity at 1 second? That's a bit difficult. You can go and draw a tangent, but you don't do that in maths anymore. So we are not going to look at tangents. You learned in ticket timers that the instantaneous velocity is reached in the middle of the time interval. So if I go and work out V average, now remember also V average is the total distance or the total displacement over the total time. I hope you remembered that from last year because you're going to have to do that a bit in the examples. So the total displacement over the total time, that you can read easily because that's going to be my 18 there and my total time is 2. And that gives us 9 meters per second. Now, where does it reach this 9 meters per second velocity? Would be in the middle of that time interval. So it reaches this at the instant of 1 second. So if I asked you for the instantaneous velocity at 1 second, you just go and look what interval is 1 in the middle of. And you go and calculate that velocity because it will give you the instantaneous velocity at 1. And that is the knowledge that you need to remember from ticket timers in grade 10. So that was position time graph. If we look at a velocity time graph quickly, this example here, I'm going to do a next video where we go from drawing a graph of displacement time and a graph of acceleration time from a graph like this. Otherwise, this video is going to get too long. So I'm just going to quickly talk through this one, and then you are going to do some examples. You can't listen to me the whole time. So if you look here, the velocity is increasing. So that means here there is a positive gradient, so there is an acceleration. My object is speeding up. If you look at this bit here, there's no change in the velocity, but remember the object is not standing still because it's still traveling at 12 meters per second. It's just traveling at a constant velocity and therefore there will be no acceleration. You can go and work out these accelerations again by getting the gradient. This little bit here, now you can see the velocity is decreasing. It was at 12 and then it becomes 6 here. So it's going slower, 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 and then it's going faster, faster, faster again. Now, there's two things I can use of this graph. Remember, the gradient is the acceleration, and I can also ask you for the displacement. Now, there's one thing I want us to look at here. So if we look at the displacement, it's the area between my line and my x-axis. So it will be this area here. So please, when you do this question, write displacement equals area. For just writing that, you basically get a mark. Then what I like to do is put my shapes because it's that block or triangle plus this block here. And then here you're welcome to use the trapezium if you know how to do the area of a trapezium. But otherwise, just split it up into little pieces that you can deal with. But please remember, it's not just that little bit. It's this block as well as that block. So for this one, it would have been quite tricky and we probably wouldn't ask you the area for the whole thing. We would say do the area up to 8 seconds or what is the displacement up to 8 seconds or something like that. And now you go and work out all these areas and you add them up. Just one thing. If we ask you for the average velocity, please remember that, like I said on the previous one, the average velocity is going to be the total. So you can't go and add up values and divide them. You have to go get the total displacement, which you would have gotten here if you did this question. And if your teacher wants to, you're welcome to stop this and actually go and work it out and get the total displacement divided by the total time, and that will give you your average velocity for this whole movement. Okay, I didn't do many calculations here. I just want you to understand the concepts again and revise the concepts so that we now can go and practice this again. So your work for now is going to be to go and do the questions 1, 2, and 3 that's on the worksheet that I've given you. Only questions 1, 2, and 3. Then in the next video, I will show you how to, or remind you how to go from one graph to another. This is just to refresh your memory about all the graphs you have. So on page 216 in your notes, please look here, because please go look at it. This is a bit faint, but you have it in your book so you can go and look at it in more detail. It just tells you exactly what I've just said. If you have a displacement time graph, you've got 3 options. It could be a straight line, a curve up, a curve down. What you can use from the displacement time graph is only the slope. So the slope will give you velocity time. The slope of the velocity time graph will give you acceleration. And these examples just follow through from the top, and you can see what this will be when it goes to velocity and acceleration. When I have an acceleration time graph, the area underneath the graph will give me velocity. I didn't really look at that, but you can see here it's meters per second times by second, so that, or meters per second squared times by seconds, so that's going to give you meters per second. This one is not often asked. I did give you an example so that you can practice it. It's not often asked because they have to give you a lot of detail if they give you an acceleration time graph, as you would see in the examples. The area of the velocity time graph, again, would give you the displacement. So you can go down like this with the slopes, up like this with the areas. So it's a good summary of everything that I've just tried to refresh your memory about. Please remember to ask your teacher if you're stuck and there's something that you don't remember. But I will go in the next video through how to draw a graph of displacement time when you have a velocity time graph, or an acceleration time graph when you have a velocity time graph.